Just imagine this for a second. You're 60 miles above the surface of the moon. You're hurtling over it at an incredible speed. And there's no air up there, which means no air brakes, no parachutes, absolutely nothing to slow you down except gravity pulling you closer and your engine. So let's get right into it. To have any chance of surviving the landing, the astronauts had to slam on the brakes. But here's the thing. The lunar module, it didn't have brakes, not in any way we'd recognize. What it had was this brand new, revolutionary, and honestly kind of terrifying piece of tech. So the big question is, what if that one critical piece of hardware failed? The whole problem really comes down to this number, 3,800 miles per hour. That's how fast they were going. That's the speed you have to bleed off in the total vacuum of space with nothing but raw gravity yanking you down. You see, this isn't just a challenge, it's a desperate fight against physics itself. And the stakes? Well, they couldn't be higher. If you do absolutely nothing, if that engine fails, you hit the surface at the speed of a rifle bullet. Game over. Without a way to precisely, delicately fight against that constant pull of gravity, the mission doesn't end with a small step. It ends with a brand new crater. The only thing standing in the way was the lander's descent engine. Okay, so this brings us to the absolute core of the engineering nightmare. See, back in the 1960s, liquid rocket engines were just not built for the kind of delicate touch you need to land on the moon. Nope. They were built for one thing and one thing only: pure brute force. So here's the best way to think about it. A standard rocket engine is basically an on-off switch. You light the fuse, and boom, it goes full blast, 100%, until it runs out of fuel. But to land on the moon, you need a gas pedal. You've got to be able to gently adjust your thrust, throttling down as you get closer and lighter. You need finesse. You need control. And here's exactly why you couldn't just, turn down a normal rocket. If you tried, you'd trigger something called combustion instability. The engine starts to, cough is the best way to describe it. These are violent, explosive pressure waves that can literally shake the engine so hard it tears itself to pieces. An explosion wasn't just possible, it was the most likely outcome. So NASA's solution had to be completely radical. They basically invented a whole new type of engine, the Descent Propulsion System. It used this really clever little device, a pintle injector, that could actually slide back and forth to smoothly change the flow of fuel. Now, this wasn't just a small improvement. This was the first major throttleable engine in the history of spaceflight. And for the Apollo crew, it was, quite literally, their one and only brake pedal. So it's one thing to have this incredible new tech, right? But it also created a massive single point of failure. What happens if it breaks? What if that throttle, their only way to slow down, suddenly jams right in the middle of the most critical part of the entire mission? Let's walk through the first and maybe most obvious scenario. It's also the most horrifying. What if the throttle jams completely shut? What if all power just cuts out? The result is immediate. It's catastrophic. The engine just dies, and the lunar module is now in total free fall. And you gotta remember, this thing was shockingly fragile. We're talking aluminum sheets so thin you could literally poke a screwdriver right through them. In free fall, it's just a tin can. The crew would be gone in seconds. Okay, but what about the opposite problem? This one's a little less intuitive, but it's just as deadly for the mission. What if the throttle gets stuck wide open, blasting at 100% thrust when you're just trying to gently touch down? Well, you're just coming in way too fast. There's no time to hover, no chance to pick a safe landing spot away from all the craters and boulders, the guidance radar can't get a proper lock, and the flight computer is just completely overloaded with bad data. Armstrong would have had zero choice but to slam the abort button and blast back into orbit. The mission would have failed, literally moments from success. But believe it or not, the drama doesn't stop there. Even after they solved the throttling problem, the engineers discovered this hidden killer lurking deep inside the fuel lines, something that almost doomed the entire engine before it ever even got off the ground. It had this kind of goofy name, Pogo Oscillation, but it was anything but funny. As the engine throttled up and down, fuel would start sloshing in the feed lines. And if that sloshing just happened to sync up with the lander's own natural vibration, the whole ship would start to shake and bounce, just like a pogo stick, creating this incredibly dangerous feedback loop. So here's how this vicious cycle worked. The engine throttles down, which causes the fuel to slosh around. That sloshing then hits the perfect rhythm, syncing up with the ship's natural frequency. This makes the engine's thrust start to flutter, which, you guessed it, makes the fuel slosh even more. It just keeps building on itself, getting worse and worse.
And this is the part that is just truly terrifying. During the unmanned tests, they realized the pogo vibrations could get so intense, they would shake an astronaut's eyeballs so hard that their vision would blur. They would be physically unable to read their own instruments. Think about that. You can't see. You can't fly the lander.
So yeah, they needed a fix, and they needed it fast. The solution they came up with was an absolute stroke of engineering genius. They decided to inject helium gas directly into the fuel lines. These little bubbles of inert gas acted like a shock absorber, squashing the vibrations before they could build up. It was this brilliant last-minute patch that basically saved the entire landing. You know, we've all seen that iconic footage of the landing. We hear Armstrong's calm voice. We see the dust kicking up. It all looks so serene. But this quote, this really captures the reality of what was happening under the hood. It wasn't some graceful descent. It was a controlled fall. It was a terrifying balancing act on top of a vibrating, potentially explosive engine that had never, ever been used like this before. So that incredible throttling engine, that was the secret to getting down to the lunar surface. But it kind of raises an even crazier question, doesn't it? How did they get off the moon? Because the ascent engine that blasted them back into orbit was so simple, so brutally reliable, that it was actually impossible to even test it on Earth. And that, well, that's a story for another time.